thanks very much for the invitation, and it's nice to see people, even if it's just digitally. So this is joint work with Noam Berger, who's at TUM, and Evitar Prokachia, who's at Technion and Texas A&M. So I'll start with a little bit of a physical motivation. So the reason people are sort of interested in studying random growth comes from physical experiments such as shown in this picture. So what's going on here is right in the middle of the picture, you can see there's an electrode, and it's sitting in a copper sulfate solution. And what happens is positive ions diffuse all around the solution until initially they sort of hit the electrode, at which point they stick. And then as the cluster starts to grow, these ions sort of diffuse around until they sort of hit parts of the cluster, and then they stick to that. And so you can sort of see that that you're getting some model that's sort of growing a particle at a time in some random way that depends on where diffusing particles hit the cluster. And what you might expect to happen in a situation like this is, because it's completely isotropic and the particles are just diffusing all over the place, you might expect that the electrode just gets coated uniformly on all sides, and it just grows in like a sort of growing disc or growing ball. But as you can see from this experiment, that's really not what's happened. Instead we've really got some sort of random fractal looking structure with sort of deep fjords and long fingers. And so this has sort of been of interest for a very long time. Why the anisotropy breaks down in this time, what's actually going on to cause this sort of random behavior to be so dominant. So the first way to sort of start thinking about this model is on a lattice. So we start off with a sort of seed, which corresponds to the electrode, and then we release our particles far away, and they perform random walks on the lattice until they become adjacent to the seed particle. And so you can sort of see this particle random walking, becomes adjacent, and then it sticks to it. And then you release another particle far away, and again it performs a simple random walk on the lattice until eventually it becomes adjacent to the cluster, and again it sticks. And so this gives us a way to simulate this model, and this lattice structure was proposed by Witten and Zander in the early 80s. And what happens is you sort of do this for a long time, your cluster gets bigger and bigger, and you end up with something that looks a little bit like this. So thanks to Vincent Beffara for this picture. And so you can see the simulation's not a million miles off what we saw with the physical experiment. Certainly we're picking up these sort of deep fjords, big fingers, kind of ferny, fractally type of shapes. So having constructed a model for this, what can we actually say about this model? Well, unfortunately, the answer is really not very much. So in the 40 years since it was first formulated, essentially the only result is a result due to Harry Keston from 87, where he proved that DLA is contained in a ball of radius t to the 2/3. So if you've got t particles, it's the ball in which it's contained, the scale's like t to the 2/3. And actually that's really quite, even though that's the only rigorous result we have, that's actually quite a weak result. So I mean, it certainly rules out that the limit is a long kind of straight line, but it doesn't tell us that the limit couldn't just be a disk. And as I said, that's the thing that we're really interested in, is to understand that DLA, well, first of all, to show it can't be a disk, and actually there's nothing, no one's come anywhere close to trying to understand that. So there's absolutely no proof that DLA doesn't converge to a ball, even though, as I said, when you look at it, it really doesn't look anything like it's converging to a ball. In fact, the problems are even bigger than that. I mean, we don't even know that a limit cluster exists. So one of the main open problems is the existence of a universal limit. And then if you could prove that existence, then the growth rate of the cluster, the structure of the limiting set, for instance, the fractal dimension, or the number of arms, all become interesting questions. So this is one of the shortcomings of this lattice approach, is it's very easy to describe the model. It's relatively easy to simulate the model. It's a little bit slow, but you can do it. it's almost impossible to mathematically study this model because we've got very few tools that apply in that setting. And there's one final problem with modeling things on the lattice, and this is what happens if you simulate large clusters. So that first cluster I showed you was cluster of size 2000. Now we get a cluster of 4000, and you can see suddenly it looks really quite different. The sort of plus sign has appeared here. And so what we seem to be seeing there is actually the underlying lattice has become visible. And if you simulate it on a triangular lattice, you see that shape underlying it. And so the reason we wanted to study DLA is to understand how this isotropic behavior breaks down. If we're studying it on the lattice, even if we could understand why that isotropic behavior breaks down, it might just be because it's on a lattice, and that's actually not telling us anything about the physical, copper sulfate model. And so that suggests that actually, well, two reasons why we should move away from thinking about a lattice. One is we actually can't say anything interesting because it's too hard, and the second one is actually the model picks up features that we don't want. Okay, so how might we go about modeling this process in an off-lattice kind of way? So here's a relatively simple idea. So start off with again with a seed particle at the origin. And this time, instead of, we've got no lattice, so we can't do simple random walks. Instead, we release particles very, very far away and let them perform Brownian motions until they hit. Then you stick a disk on at the point it hits, release another particle, let it do a Brownian motion until it hits the cluster, and stick it on, etc. And so you start to see a picture like this. Okay, so how do we study this model? Well, certainly it's isotropic. There's no problem with that. But if we want to study it, essentially what we need to be knowing is where on this cluster the next particle is going to be landing at each point in time. So we need to know the hitting distribution of Brownian motion on the boundary of this cluster. And as you can see, this cluster is quite irregular. And so trying to work out what the hitting distribution is not completely straightforward. But there are a few things that can help us. And in particular, if we restrict ourselves into 2 dimensions, the hitting distribution of Brownian motion is conformally invariant. And so what do I mean by that? What I mean is if we mapped the exterior of this cluster to the exterior of another shape, if we had a conformal mapping that did that, and then we looked at the trace of a Brownian motion coming in until it hit the cluster, and we looked at the image of that trace under the conformal mapping, that image of the trace would also be a Brownian motion. And so a natural thing to do is to sort of consider a map that goes from the exterior of the unit disk to the exterior of this cluster. And we know such a mapping must exist by the Riemann mapping theorem. What's the hitting distribution of a Brownian motion on the exterior unit disk? Well, because everything's completely isotropic, the hitting distribution must be uniform. And so where are we going to attach our particle in this picture? Well, we just map to the image under this map of that uniform point. And so that's essentially what I've done here. And so just a bit of terminology, we call harmonic measure the measure of the hitting distribution of Brownian motion on a cluster boundary, as seen from infinity. By conformal invariance of Brownian motion, harmonic measure and conformally invariant. And so that gives us this algorithm for sampling at a boundary point on this very irregular set. Okay, so what's the difficulty with this idea? Well, it's trying to find this conformal mapping F. So, if I've got this sort of cluster, how on earth do I find a map from the exterior of the disk that maps into this boundary? That's again with very irregular boundaries, it's not at all easy to do that. So what we want to do is to sort of come up with an algorithm for constructing that mapping. And in order to make this algorithm a little bit easier, we relax some of our requirements. So in this picture, we've made all the particles are sort of identically shaped disks. Maybe it's not so important that the shapes are exactly the same. So there's a few problems with disks. So you can see, for instance, what if we got if we sampled a point that was sort of deep in this little cluster down here? You can see my mouse. Sorry. then actually we can't even attach a disk in there. There's no space. So there's certain problems with disks. And the other problem is disks don't behave that well under the kind of conformal mappings that we're going to be considering. So we just relax our assumptions a little bit and say, well, if we can have a model that describes aggregation of particles that we can construct in an algorithmic way, that's going to be good enough. In particular, if we can insist that the particles are roughly the same size. And so here's the construction. So we start off, as I said, our relaxations is it's just technically easier to let our particle be a little slit rather than a ball. That avoids this problem of not being able to fit it into little spaces. And another advantage of having our particle as a little slit is that we can explicitly write down the mapping, the conformal mapping from the exterior unit disk to the exterior unit disk without the slit. And we want that mapping to fix infinity because that's where we're going to release our, that's where our harmonic measure is coming from. And one final requirement, we don't want to have sort of rotations at infinity, so we want the derivative to be sort of to be a real at infinity as well. And another way of saying that is we can write this mapping as a complex mapping from the exterior unit disk to the exterior disk without this particle in the form some real number greater than 1 times z plus an order 1 quantity. And we call this, because this is greater than 1, we can write it to e to the c for some c greater than 0, and c has a name. It's the logarithmic capacity of this cluster. And if we wanted our slits to be of length delta for some small delta, there's an exact correspondence between capacity and the slit length. And so in the remainder of the talk, I'll sort of interchangeably move between delta and c. Sometimes it's convenient to talk about the slit length. Sometimes it's convenient to talk about the capacity. If you're not happy with capacity, just think of it as a measure of the size of the slit. So it's just a function of the size of the slit in this way. And in particular, small capacities correspond to small slit lengths. Okay, so that's how we construct a single particle. How do we construct an algorithm for, so that's how we come up with a map corresponding to a cluster with a single particle. Well, how do we construct a map corresponding to several particles? Well, the process is recursive. And so here's a description, but I'll show you a picture on the next page, which makes it easier. So what we need a sequence of particles, which we describe by their capacities or their lengths, and we need a sequence of attachment angles corresponding to where we're going to put them on the cluster. And if we know the length of the slit, we can obviously write down a mapping, as I said before, corresponding to that slit of that length. And in order to attach at different places, you can just conjugate by rotation. So to correspond to getting the particle at the right angle. And so that gives us a sequence of conformal mappings Fn corresponding to each of these particles. Okay, and then we just we start off with our conformal mapping being the identity maps, and that takes the exterior unit disk to itself. So that corresponds to a cluster which just contains the seed particle and nothing else. And then recursively we precompose. If we've got a particle map corresponding to n-1 particles, we precompose with the Fn map. And what I'll show you in the next picture is that actually constructs a sequence of conformal mappings from the exterior disk onto the exterior of clusters with the property that the clusters are strictly increasing compact sets. And that's the property we want. So here's some pictures just to make it a little bit easier. So supposing we found our mapping phi n-1, our conformal mapping from the exterior unit disk to the exterior unit disk of this cluster minus the n-1 particles. What I do next is I precompose with the mapping corresponding to my nth particle. So how do I describe my nth particle? It's got a capacity Cn and it's attached at an angle theta n. Well, what happens if I compose these two mappings? Well, I know that phi n-1 maps the exterior of this circle to the exterior of the black cluster. And I know that this blue particle, this nth particle, lies in the exterior of that unit disk. And so it must lie in the exterior of the black cluster, but it's also attached at a single point. And so it must be attached at a single point. And so the image of this blue slit now becomes the nth particle. So we had n-1 particles in the black cluster. So the black cluster union with this blue curve. Now you can view it as having n particles, and so that gives us this relation. So how do we construct a sequence of conformal mappings corresponding to growing clusters? Just using this recursion that phi n is the phi n-1 map precomposed with fn, and if you run that recursion through, you can just see it's just the composition of the n individual maps corresponding to each particle in this order. As I said before, we paid a price for this. So we now have a way of constructing these conformal mappings very, very explicitly. We just need to know the angles and the capacities. But what we've lost here is we've lost control of the shape of the particle. They're no longer little slits. They've turned into curves. The conformal mappings distorted them, and the size is also distorted. So the length that we had here is not the same as the length of the curve that we have over here. So that's the price that we pay. But the benefit is that we actually have a way of constructing these mappings just given a sequence of angles and a sequence of capacities. And so by choosing our angles, and well, I've changed from capacity to slit lengths here, but in different ways, we can construct a really wide class of growth models. So how should we choose these sequences to correspond to DLA? Well, if we think here, well, what heating distribution do we want on this cluster? Well, we want harmonic measure. Well, what does harmonic measure correspond to? That corresponds to a uniform distribution in this picture. And so we need to be picking our thetas IID uniform to get DLA. So that's kind of easy. Well, what about the slit length? How do we choose the length of the slit? Well, again, for DLA, for it to be physical, we kind of want all our particles in the right-hand image to be roughly the same length. And so if you think about, well, what kind of distortion does the phi n map impose on this CN? Well, we can do an arc length computation in this picture. And if you do the arc length computation, you'll see that the length in this picture is just the modulus, well, the integral of the modulus of the derivative of phi n-1 integrated along these values. And for small particles, which is what we're going to be thinking about in physical situations, under the assumption that the derivative doesn't change too much along this length, you can think of the distortion as being approximately the derivative of this map at the attachment point, e to the I theta n. And so if we want to choose a length in this picture, that means all our particles in this right-hand picture are roughly the same size. We need to pre-multiply by the modulus of the derivative at the attachment point, and so that's what's being done over here. So just fix some parameter for length delta. If we choose our nth slit length to be that parameter divided by the derivative at phi n minus 1 at the attachment point, then when you apply that map phi n minus 1 to that slit of length delta n attached at that point e to the I theta n, it gets this length delta n gets multiplied by phi prime, and so the image is roughly of length delta. And so this is a sort of choice of parameters that corresponds to the sort of physical DLA model that we want. Hastings and Levitov sort of proposed this model in '98 to grow well as a candidate for an off-lattice version of DLA, but they didn't just propose the model for DLA. They decided to generalize the model a little bit. Instead of taking this power to be -1, they took this power of the derivative to be minus alpha over 2 for alpha between 0 and 2. And so taking alpha equals 2 exactly corresponds to their candidate for DLA. But the advantage of allowing a spectrum of values is that they argued that you actually capture other interesting growth models in the process. They argued that alpha equals 1 corresponds to biological growth, like if you think about how molds or lichens grow. and alpha between 1 and 2 sort of corresponds to things like lightning strikes. So that was one reason why they introduced this parameter. And there's a second reason which has been really helpful to us mathematically, which is if you imagine the case when we set alpha equals 0, then we're just taking our delta n's to be equal to delta in each case. And so each of our maps Fn is just a map corresponding to a slit of length delta rotated by some IID angle theta n. And so each of these mappings is IID. And so we have a Markov process over here. So our phi n is a Markov process, and that makes it easy to understand. And so as mathematicians, what we sort of hope is, well, if we can understand the alpha equals 0 case, and we have a way of interpolating between the simple case and the model that we're really interested in, maybe we can sort of push along this interpolation and start to understand the physical model. Okay, so that's the description of the family of models that Hastings and Levitov proposed. And so what's known about these models? Well, as I sort of indicated, almost all the easiest model, or the mathematically most tractable model, is this HL0 model, where all the particle maps are IID. And so almost all the previous work relates to this model. Some examples. So in 2012, there's a paper with James Norris and mine where we show that the scaling limit of HL0 is a growing disk, and the rate at which it grows is sort of e to the Cn, where C is the capacity of the base particle. So it doesn't look like DLA. As I said, we don't see those fractional behaviors. It is just a disk. But it has quite an interesting internal branching structure, which is related to the Brownian web. But the main problem with it is that the expected size of the nth particle is roughly delta times e to the Cn. You can sort of see that the derivative of phi prime is e to the Cn, and so the distortion that we get is exponential. And so it's a really unphysical model. As the model grows, the particles get bigger and bigger on the outside, and so even though we can mathematically study it, it's never going to correspond to anything that physicists are interested in, unfortunately. Other work is in 2017, notoriously showed that the fluctuations around that unit disk converge to a log correlated fractional Gaussian field. Now, in the case when alpha is not equal to 0, all the results that exist require regularization. So what do I mean by that? Well, this derivative is a derivative of a very rough cluster. You know, it's consisting of it has lots of singularities at the tips of each of these points. And so the derivative, and singularities at the base. And so the derivative can take the value 0 and infinity. And so this map is really difficult to control on the cluster boundary, and that makes this very difficult to study, because a priori you don't know whether you're attaching a particle whose preimage is size 0 or whose preimage is arbitrarily large. But what we can do is, instead of evaluating this map on the cluster boundary where it's really badly behaved, we can just push it a little bit away from the cluster boundary. So if you imagine just drawing a little circle of radius r just outside this disk and looking at the image of that circle around this cluster, and we could evaluate the derivative just off the boundary, and that makes this mapping much better behaved. And so this is what we call a regularization, and almost all the existing results for HL alpha with alpha non-zero are in some regularized setting. And so the main results are in 2005, Stefan Roeder and Michel Zinsmeister found estimates on the dimension of scaling limits for a regularized version of HL alpha. In 2015, Alan Sola, Frederick Wickland, and myself got the scaling limit for a sufficiently regularized HL alpha model. In fact, we showed it was a growing disk for all values of alpha. And really what that told us is that if you want to be seeing these sort of fractal types of behavior, you actually can't regularize as much as we did. So you really, the regularized approach needs to be done very, very carefully if you don't want to throw away all the interesting behavior. So that's kind of what that result tells us. And then my PhD student, George Little, when I 2020, found the fluctuations for a very regularized HL alpha. So in fact, we regularized at infinity. which means that this derivative just becomes deterministic, and again, that makes things a lot easier to study. So that's the sort of state of play of these growth models, conformal growth models, where you're seeding them on a disk corresponding to the unit circle. But that's not the only situation that physicists might be interested in. So what I'm showing here in this picture is we've got a lithium battery. It's a sort of cross section of a lithium battery, and as you can see on the surface, it's starting to grow these dendrites. So ions are diffusing out of the solution that's inside the lithium battery, and they're attaching themselves to the boundary. And this is really, really bad news for batteries. It's the main reason that batteries start to perform worse and worse the more and more every time you recharge your battery, the performance gets worse and worse. And the sort of biggest problem that can happen is one of these dendrites can get so long that it touches the other side. Then it can short circuit, or in extreme cases, it can even sort of punch through the other side and cause fires. And I don't know if you remember a few years ago, the Samsung Galaxies kept spontaneously catching fire. One of the conjectures for why that might have been happening was to do with these dendrites. So these are really, really bad news in batteries, and a lot of efforts put into trying to come up with ways to design batteries that will limit the rate at which these dendrites grow. So this is a really important question for physicists to try and understand the growth of dendrites in this kind of setting. And well, what's the difference between this picture and the copper electrode picture? Well, the copper electrode was seeded on a disk. In this case, we're seeded on a line. And so that asks the question: well, can we come up with some of the models that we did before, but seeded on a line rather than seeded on a disk? And so, yeah, certainly the lattice model is no problem with that. Again, just release your particles from infinity, let them perform, or from very far away, let them perform simple random walks until they hit the boundary, and then they stick. And here's a simulation of the sort of DLA that you get if you do that. And again, you can see for over a small amount of lifetime, this is a pretty good description of what we're seeing over here. You sort of start to see similar features: some taller dendrites, some sort of big gaps, some deep fjords and fractals forming. Okay, so this model of stationary DLA was constructed by Eddie D'Abracaccio and some co-authors. Can we do the same? But it suffers from the same problems that the lattice. Well, it's a little bit easier to study than the lattice model seeded from a single particle, but still we suffer from the fact that there aren't many tools which work in these lattice settings. So that then begs the question: well, can we construct a conformal version of a stationary off-lattice type DLA model? And there's actually a second reason why we might want to do that. So let's just think about the standard HL0 process. So we've got a disk, and our first particle arrives of length delta. But that's exactly the same. We can just by changing our scale, we can rescale this to make the particle have size 1, and in this case the disk is going to have radius 1 over delta. And so you can see sort of as you let delta go to 0 and just sort of look at where this particle has landed, this converges more and more to sort of having your disk kind of turns into the lower half plane, and you're sticking sort of slits of length 1 onto that. And so if we did have a stationary version of Hastings-Levitov in a way that would capture the sort of local behavior of the HL0 process. And so that's a sort of second motivation for why we might want to study this. Okay, so what exactly do we want to construct? Well, we want to construct a stationary model, and I should make this clear. This is the stationary in space, so stationary under shifts, under spatial shifts. we want it to be made up as a composition of conformal mappings from the upper half plane to subsets of the upper half plane. And we want our measure to, in a way, correspond to the uniform measure that we had on the unit disk. And obviously, we don't have a uniform measure on an infinite line. But what we can do instead is we can construct a Poisson point process time is 0 to infinity. So Poisson point, if we view sort of time crossed with space, we can construct a Poisson process in this space-time. And the idea would be that at a point, if a Poisson point was at place position x at time t, at that point we want to grow a slit at position x of size 1. So somehow the Poisson point process is going to capture the times of arrivals and the positions of arrivals. And because Poisson point processes are sort of stationary in sort of space, this should correspond to a sort of generalization of picking uniformly on the unit disk. And then lastly, we just need to sort of get things going. We need a mapping corresponding to a single particle. Let's just attach it to the point at the point 0. And actually, one nice thing about the upper half plane is actually it's very easy to write down a mapping which takes the upper half plane to the upper half plane without the bit of the imaginary axis from 0 to I, so corresponding to a slit of length 1. It's just given by this formula here. You can just check that easily. And the only thing you need to be careful about is just picking the right branch of the square root to make sure that the left half of the upper half plane maps to itself and the right half maps to itself. But if you get the branch of the square root right, then this is the formula. And then lastly, instead of rotation, which we had with our slit map on the disk, we need translation so that we can, instead of attaching our slit map at 0, we want to attach it at any point x. And so we can just do that by conjugating with translation. Okay, so we've got the sort of ingredients that we want. The ingredients being we've got a Poisson process indexed by a Poisson process on space-time, and we've got a family of slit maps that attach slits at all points along the real line, slits of length 1. Okay, so here's the axiomatic definition of our stationary HL0 process. So we say that a Cadillac process that takes time to a family of conformal mappings, F indexed by T, is called a stationary Hastings-Levitov 0 if it satisfies the following 3 conditions. So first of all, we want an initial condition that at time 0, we just have the identity map. Well, what does that do? That takes the upper half plane to itself. And so that corresponds to a cluster which has no points in that. So we're just starting with our seed just being the real line, and there's no particles. The second condition we want is a sort of adaptedness condition. So what happens if we take our map FT? Well, what does that do? That takes the upper half plane to the upper half plane without the cluster that's there at time t. Well, what does Fs inverse do if S is less than T? Well, that takes the bit of the cluster that was there at time S and it maps it back down into the upper half plane. And so what you're left with is only the bits of the cluster that arrive between times S and T. And we want that to be measurable according to our Poisson process, corresponding to Poisson points in the interval that arrived in the time between S and T. So what the cluster does between times S and T should only depend on Poisson points that have arrived in the strip corresponding to time being between S and T. And then lastly, we want a growth condition that tells us that if there is a Poisson point, we want our map to change by composition of a slit map. And we've written it down in this slightly unusual way. So let ATN just be the Poisson points that arrived up to time t, but only between minus x and x. And then we've sort of written our map as a sort of limit of a sum of a difference. This looks a little bit weird, but if you just imagine, supposing that we didn't have infinitely many Poisson points, supposing that this was just a finite sum, and you could just order the times of arrivals. then it's just a simple telescoping argument. Just tells us that ftz is just ft minus composed with the particle that arrived, or supposing there was a particle that arrived at t, ftz would just be the ft minus composed with that particle at time t, and if there was no particle at time t, then ft would just be equal to ft minus. So this is the sort of, if you sort of unpack this and cancel all the telescoping, this just gives us the same composition of mappings that we had in the unit disk. So the only way that a map can change is when a Poisson point, when there's a Poisson arrival, it changes by composing with a slit map corresponding to being at that position. So why have I written it in this slightly weird way rather than just saying that? Well, the problem is that Poisson points in any strip, no matter how thin it is, there are infinitely many Poisson arrivals. And so essentially particles are arriving all the time. And so you can't really sort of say, you can't really order the particles in a time ordering. And so we need to sort of pick an order in which we want to do it. And the advantage of picking this order, where we limit to particles that arrive between minus n and then just let n go to infinity, is that this preserves symmetry. If we chose a different order, you would end up getting drift. And the reason for that is that the sum is actually not absolutely continuous. So it's really sensitive to the order in which we sum it. So this particular order seems natural to us because it respects left-right symmetry. If you chose a different set, so for instance, x between minus n and 2n, you know that your whole cluster would start to get a drift. And so I know this is kind of technical, but it's the fact that the sum is not absolutely convergent that actually makes this model quite difficult to study, but also gives it most of its interesting behavior. Okay, so that's what we want. These are the properties that we want our definition to satisfy. But the question then is, well, does a process like this exist, and is it unique? And this is really a non-trivial problem, as I said, due to these dense set of arrival times. You know, particles are arriving all the time, and so it's actually very a lot of our paper is actually proving the existence of this process. But yeah, we can prove it exists and it's unique. And essentially the proof is by construction. So what do? Well, we construct an approximation that only consists of the arrivals in this set A of particles that arrived at spaces between minus n and n. Then on any finite time interval, there are only finitely many of those, so we can order them. And once we can order them, then we can just construct our composition, our map as a composition of these slit maps in almost exactly the same way as we did on the disk. Just we're using the slit maps corresponding to the upper half plane rather than to the disk. So we can construct the sequence of approximations, and then what we need to show is we need to show that this is a Cauchy sequence in the topology of mean squared convergence on compact subsets, compact time intervals, and then because we have a Cauchy sequence, we know that a limit exists, and lastly we can check that the properties that we described in our axiomatic description actually hold for this limit. So I've sort of just given a little idea of this of the structure there, but you know there's quite a lot of work involved in that. Okay, and here's a simulation of what this sort of stationary HL0 can look like, and yeah, I think that's all I'll say for now. So that we can it sort of looks like this. Well, what about properties of this? So the first thing that you notice is that to leading order this seems really quite flat. So this is a big difference between the stationary DLA, where you can see it's really not flat, and this simulation that to leading order this is flat. And in a way, if you think about the sort of zooming in idea, that somehow this corresponds to zooming into a little bit of the round HL0, this is maybe not so surprising because, as I proved with James, that HL0 converges to a disk, and so if you zoom in, you would expect a flat interface. But one of the nice properties of having a flat interface is that the well, it's flat and it's sort of it doesn't distort anything. Is that if you look at the derivative of ft, it's approximately 1, but the derivative tells you about how much distortion your particles are going to get. And so if the derivative is approximately 1, that means that really you're not going to get very much distortion at all. And so the distribution of the particle size is tight in this case. And this compares really favorably to the classical HL0 in the disk, where we showed that the map grew exponentially, and that meant that the particle sizes were distorted exponentially. And so that means that this model has good physical properties. And so unlike the classical HL0, this could be a candidate for DLA grown on a fiber. And if you look in this picture, you can kind of see that property. So these little sticks where it lands right on the disk are of sort of height 1, just to sort of give you the scale. And then if you look at the ones that arrive sort of on the cluster boundary, they also seem to have size of roughly the same shape. Whereas if you looked at a similar picture for the classical HL0, you'd really see that the outer ones were exponentially larger than the small ones. Okay, so it's got good physical properties, and that means that it's actually a candidate for off-lattice DLA, and that means that maybe we can actually use it to study properties that we feel that maybe DLA should have. So one thing that we are interested in is, as I said, harmonic measure is kind of tied up in a lot of the study, and we can write down harmonic measure very, very easily for these conformal mappings. It's just the inverse of two maps. So if I just go back to this picture, suppose I take 2 points on the real axis, and I ask, how much harmonic measure is carried by the cluster that's growing between those 2 points. Well, I just take the pre-image of those 2 points and look at the difference between those, and that tells me how much harmonic measure we have. And what you can show is that for all intervals, this is a positive martingale, and so under certain conditions, you can prove it converges. And what we're able to do is we're able to show that it converges to 0 almost surely. And so what does that mean? It means if you take any interval on the real line and you look at the cluster that's growing inside that interval, and you ask, well, what happens as the cluster, as time goes to infinity? Well, the harmonic measure going to 0 means that the bit of the cluster between those 2 points is going to stop growing. And we can think of the bit of cluster that grows between this as a union of trees, where each tree corresponds to a particle that initially attached to the real line. And so that tells us that all trees are finite. And again, you can see that in the picture. So if we look sort of between, say, -5 and -15, we've got the sort of pale blue forest growing, which has sort of 4 trees in it. And you can see that what happens is once we get to time about 15, the 2 trees on either side of that cluster of that forest have sort of encroached, and Brownian motions coming in from infinity, or particles coming in from infinity, aren't going to be able to attach to that bit of the forest anymore. And this, so our result telling us that all trees are finite means that even these 2 bigger trees which have encroached, eventually there'll be 2 even bigger trees on either side of them that are going to encroach, and no tree that starts on the real axis has a chance to grow infinitely, to grow forever. It's always going to get overwhelmed by, or shaded over by, the trees on either side. What else can we say about this model? Well, if we think about things from a physical point of view, we're sort of interested in situations where the particle sizes are typically very, very small. So in this model that we constructed, all our particles had size 1. But what about attaching very, very small particles and running the process for a long time? Well, so how do we do this? Well, we can just attach particles size delta and attach them at times of a rescaled Poisson process, delta P, where P is our original Poisson process of rate 1. And just by scale invariance of the upper half plane, it's equivalent to the original set of maps F under rescalings of space and time. So we rescale time by delta to the -1, corresponding this Poisson process, rate changing, rescale space again corresponding to the Poisson point process changing, and then multiply the delta in front corresponding to the particles being of size delta. So each particle needs to be squashed down a little bit. And what we can show is that uniformly on compacts, this does correspond to just a flat interface. So the small particle limit does just give us a flat interface that just sort of grows up linearly in time with rate given by pi over 2. What about the harmonic measure? Well, again, we can ask about the rescaled harmonic measure. Well, we know that this is a martingale, and that means that if we tune our time rescaling, so this is a delta minus 2, whereas here we had a delta minus 1, so we just need to speed up time a little bit more. Then we get convergence to a Brownian motion. So it's a martingale. If the limit's continuous, it must be a Brownian motion. Well, harmonic measure doesn't just sort of capture properties of where things attach. It actually tells us a little bit about the shape of the cluster. So a way to think about this is if harmonic measure is shrinking, that's because the cluster's kind of two trees in the cluster are growing towards each other. If harmonic measure is growing between 2 points, that means that the trees on either side are growing apart from each other. And so knowing which way each of these FT inverse maps sort of wiggles can tell us not just about how the harmonic measure changes between them, but also actually what the cluster itself looks like. And so what you can do is, using the fact that the interface moves straight upwards and that the harmonic measure behaves like Brownian motion, this tells us that every finger of growth, and so what I mean by finger is, let's just take a point from the outside and just sort of track this in until we come down to the boundary. Each of these fingers actually converges to a trajectory of a one-dimensional Brownian motion in the limit. And if we take 2 fingers that are sort of far away from each other, so this one here and this one here, they behave like independent Brownian motions until they meet, and then they coalesce. And so you get something that looks a lot like the Brownian web in that case. But we can actually get more than that from this Brownian motion description. We can actually compute the Hausdorff dimension of this cluster using just from the Hausdorff dimension of Brownian motion. And so all fingers of SHL0 have Hausdorff dimension 1.5. And for us, this was one of the most interesting and unexpected things about this model, is that exactly agrees with predictions for DLA on fibers in the physics literature. And other properties that are immediate corollaries of this is that we can sort of relate the height of the tree at various times and the number of particles. And so, yeah, we can show the probability there's a tree of height more than h emanating from interval 0, 1 behaves like h to the minus 1/2. And typically, if you have a tree of height h, it contains h to the 3/2, order h to the 3/2 particles. And so the property that there's a tree from 0, 1 with more than k particles, again, decays like k to the minus 1/3. So in particular, this the second bullet point is what's been studied in the physics literature for DLA on the lattice. And so here's a simulation for DLA on the lattice. And what we've plotted here is the log of the number of particles against the log of the height, and the gradient corresponds exactly to this prediction. And so you can see that as the height gets larger and larger, the agreement sort of gets better and better. And so this is for actual DLA on the lattice, and our mathematical results tell us that that this same property holds for our stationary Hastings-Levitov model, which again supports our claim that it can be used as an off-lattice version of DLA in a way that the original Hastings-Levitov 0 on the exterior just couldn't be used as a way of studying true DLA seeded from a single point. Okay, so I think I'm just about out of time, so I'll just stop, just finish with a few sort of open questions and conjectures. So what we've constructed in our model is the stationary Hastings-Levitov zero, where at every point we're attaching a particle whose pre-image is a slit of length 1. But what we could do is we could, actually correct for the local distortions by deriving by the derivative at that point raised to some power of alpha, and that gives us a sort of stationary version of Hastings-Levitov with some parameter alpha. And again, the questions that you've got are, is this model well defined? So once again, we've got infinitely many rivals. Plus, you've got this feedback coming in from the derivative depending on all of the previous arrivals. So is this mapping going to be well defined, or is there too many different things going on simultaneously that that it's just going to explode very, very quickly? And so our conjecture is that it should be well defined if alpha lies between 0 and 1. And the reason for that is we have some strong numerical evidence that true Hastings-Levitov behaves like a disk for alpha between 0 and 1. And if we think stationary Hastings-Levitov is kind of a zoomed in version of that disk, then that means that if you zoom into a disk, you still get something stationary. And so we believe it should be well defined for alpha between 0 and 1. If alpha's greater than 2, we believe it's not well defined. And again, if you do simulations for true Hastings-Levitov, you get very spiky clusters once you take alpha bigger than 2. They really don't even seem to have any local sort of local behavior. Between 1 and 2, it's a little bit unclear, and we're really not sure what should happen in that case. Possibly it's well defined but not unique. We're really not sure, or possibly you can find it but it's not stationary. So that we don't even have a conjecture about alpha between 1 and 2. Second question is, we've done all our work for slits, but in the HL0 model on the seated on the disk, we were able to show universality in different particle shapes. So it didn't really matter too much whether we had a slit particle or a disk or a blob or a bump or anything. And so the same question holds is, can we relax that slit assumption to allow for different particle geometries? The third open question is, can you relate stationary Hastings-Levitov to early time local Hastings-Levitov? So just in this very first sort of bits of time before we've actually converted truly to a disk. And if we could sort of prove that relationship, then that would allow us to borrow the Brownian-Webb result from HL0 to SHL0. So we could prove this directly, but if we can establish that relation, we get it for free from the work on HL0. And then lastly, thinking about Vittorio-Silvestri's proof on Gaussian fluctuations for true Hastings-Levitov, we would expect to have Gaussian fluctuations for a quantity of this form. So again, can we prove that? Okay, so I think I'll stop there.